The Earth that turned slowly in the distant future bears no resemblance to the world we know today. 500 million years have passed since the last human drew breath, since the final city crumbled to dust, since the species that once called itself the measure of all things vanished into the fossil record that no longer exists to remember them. This is a planet transformed beyond imagination, sculpted by forces so vast and patient that they dwarf our comprehension of change itself. The sun hangs in an alien sky, bloated and angry, casting harsh light across landscapes that defy every expectation born from our brief experience of terrestrial existence. Where once blue oceans lapped against familiar shores, now endless plains of crystallized minerals stretch toward horizons shimmering with heat that would have been lethal to any life form we recognize. The atmosphere itself has been rewritten by 500 million years of stellar evolution, chemical transformation, and biological adaptation pushed to the very limits of possibility. This is the Earth of deep future time, a world that represents the ultimate destination of every geological process, every evolutionary pressure, every cosmic force that shapes planetary destiny across the inconceivable spans of astronomical time. To understand this alien Earth is to confront the most fundamental truth about existence itself, that everything we consider permanent is merely a momentary arrangement of matter and energy, destined to be transformed beyond recognition by forces larger than worlds, older than life itself. The journey to this future began with the formation of our solar system 4.6 billion years ago, when gravity collapsed a cloud of interstellar dust and gas into the nuclear furnace we call the Sun. But that beginning was also the first step toward an ending, for stars are not eternal. They are vast machines that consume themselves, burning through their nuclear fuel with a hunger that grows more intense with each passing eon. The sun that warmed the first living cells, that drove the evolution of complex life, that witnessed the rise and fall of countless species across geological time, has been growing steadily brighter and hotter throughout its existence. Every second, the sun converts 600 million tons of hydrogen into helium through nuclear fusion, releasing energy equivalent to 100 billion nuclear weapons. This process has continued for billions of years and will continue for billions more, but it is not constant. As the sun ages, as the composition of its core changes through the accumulation of helium ash, the nuclear reactions become more efficient. The star grows brighter, hotter, more energetic. What began as a gentle warming that made life possible becomes an inexorable increase in radiation that will ultimately make life impossible. Over the 500 million years we're contemplating, the sun's luminosity will increase by approximately 5%. This seemingly modest change masks a transformation of devastating proportions. 5% more solar energy reaching Earth translates to surface temperatures that rise by dozens of degrees, atmospheric chemistry that shifts beyond the tolerance of existing ecosystems, and climate patterns that bear no resemblance to anything in our planet's history. But stellar evolution represents only one of the cosmic forces reshaping Earth across deep time. Our planet exists within a galaxy that is itself in constant motion, carrying our solar system through regions of space with varying densities of gas, dust, and radiation. The Milky Way rotates like a vast pinwheel, completing one revolution every 225 million years. In the time frame we are considering, Earth will have completed more than 2 complete galactic years, travelling through cosmic neighbourhoods that may expose our planet to entirely different conditions than those that have prevailed throughout recorded history. During this galactic odyssey, our solar system may encounter dense molecular clouds that could affect the sun's output and Earth's atmospheric conditions. We may pass close to other star systems, potentially disrupting the delicate gravitational balance that maintains planetary orbits. Most significantly, we may traverse regions of the galaxy with higher concentrations of cosmic radiation, subjecting Earth's atmosphere and biosphere to energetic particles that could drive evolutionary changes at accelerated rates. The cosmic environment itself will continue to evolve over these vast timescales. Nearby supernovae could bathe Earth in radiation intense enough to strip away portions of the atmosphere and trigger mass extinction events. The gradual clustering of galaxies under the influence of dark energy will change the night sky beyond recognition, while the ongoing expansion of the universe will stretch the wavelengths of distant starlight until the cosmic background becomes increasingly cold and dark. Yet even these astronomical forces pale in comparison to the transformations occurring within Earth itself. The planet's interior remains a churning engine of geological change, driven by the decay of radioactive elements that have been releasing heat for billions of years. This internal energy powers the movement of tectonic plates, the cycling of material between surface and interior, and the magnetic field that protects our atmosphere from solar wind erosion. Over 500 million years, plate tectonics will reshape the face of the Earth multiple times over. The continents will drift thousands of miles from their current positions, colliding and separating in a slow-motion dance that creates mountain ranges, opens ocean basins, and fundamentally alters global climate patterns. The Atlantic Ocean, which began opening 200 million years ago, may begin to close as the Pacific continues to shrink. New supercontinents will form and break apart, each configuration creating unique environmental conditions that drive evolutionary changes in whatever life forms survive the ongoing transformation. The formation of supercontinents represents one of the most dramatic events in Earth's geological future. When most or all of the planet's landmass assembles into a single enormous continent, the effects on climate, ocean circulation, and biological evolution are profound and far-reaching. The interior of such a supercontinent experiences extreme continental climate conditions, with scorching summers and frigid winters that push the limits of biological tolerance. Coastal areas become rare, eliminating the moderate maritime climates that support much of today's biodiversity. Perhaps most significantly, supercontinent formation affects global ocean circulation patterns in ways that can trigger ice ages or periods of extreme warming. When continents are scattered across the globe, ocean currents can circulate freely, distributing heat from the equator toward the poles and maintaining relatively stable global temperatures. But when landmass is concentrated in one area, these circulation patterns become disrupted, potentially creating feedback loops that amplify climate changes beyond the tolerance of existing ecosystems. The ocean itself faces an even more dramatic transformation over these timescales. As the sun grows brighter and surface temperatures rise, the rate of evaporation from the world's oceans will increase exponentially. Water vapor is itself a greenhouse gas, creating a feedback loop that accelerates the warming process. Initially, this will drive more vigorous weather patterns, with stronger storms, more intense precipitation, and more dramatic seasonal variations than anything in recorded history. But the process will not stop there. As temperatures continue to rise, evaporation will outpace precipitation in many regions. The water cycle that has operated for billions of years will begin to break down as atmospheric water vapor escapes to space faster than it can be replaced. The hydrosphere that makes Earth unique among the planets will slowly diminish, leaving behind increasingly concentrated solutions of salts and minerals that eventually crystallize into the barren plains that characterize our far future world. This transformation of the hydrosphere represents perhaps the most fundamental change that Earth will undergo over the next 500 million years. Water is not merely the medium in which life operates. It is the substance that makes complex chemistry possible, that enables the transport of nutrients and waste products, that moderates temperature extremes and maintains the atmospheric conditions necessary for biological activity. As water becomes increasingly scarce, life will be forced to adapt to conditions more extreme than any that have existed since the planet's earliest history. Yet life has proven remarkably resilient throughout Earth's tumultuous past. The fossil record documents survival through ice ages that encased the planet in kilometre-thick glaciers, through periods of greenhouse warming that eliminated polar ice entirely, through volcanic eruptions that poisoned the atmosphere with toxic gases, and through asteroid impacts that darkened the sky for years at a time. Each catastrophic event eliminated some species, while creating opportunities for others to radiate into new ecological niches. The question that haunts our contemplation of Earth's deep future is whether life can adapt to changes more extreme and prolonged than any in the planet's history. Can biological systems evolve to survive in a world without oceans, under the harsh radiation of a brightening sun, in atmospheric conditions that bear no resemblance to those that supported the evolution of complex life? The answer may depend not only on the creative power of natural selection, but on whether intelligence itself can transcend the biological limitations that confine it to a single planet. the possibility that intelligence may represent a phase transition in the history of life, a development that allows conscious beings to manipulate their own evolution and environment in ways that transcend natural limitations, adds another layer of uncertainty to our projections of Earth's future. If technological civilization can survive the various catastrophes that threaten its existence over the next few million years, it may develop capabilities that allow it to engineer solutions to planetary-scale environmental changes. Terraforming technologies might maintain habitable conditions on Earth long after natural processes would render the planet uninhabitable. Genetic engineering might allow life forms to adapt to environmental extremes that would otherwise prove lethal. Space-based civilizations might preserve Earth's biosphere by transporting entire ecosystems to more favourable environments around other stars. The tools of intelligence might prove powerful enough to extend the story of Earth life far beyond the natural lifespan of planetary habitability. But such technological solutions remain speculative, dependent on the survival and development of intelligence across timescales that dwarf recorded history. The more certain prediction is that geological and astronomical forces will continue to operate according to physical laws that care nothing for the preferences of conscious beings. The Sun will continue to evolve toward its inevitable red giant phase. The planet will continue to lose its atmosphere and water to space. The surface will eventually become too hot for any form of life we recognize. Standing at the threshold of this vast temporal landscape, we are forced to confront the ultimate impermanence of everything we consider solid, stable, and enduring. The mountains that seem eternal will be ground to sand and scattered across ocean floors that will themselves be lifted into new mountain ranges. The continents will drift into new configurations that eliminate familiar coastlines and create landscapes alien to our experience. The very air we breathe will be transformed into atmospheric compositions that would be toxic to current life forms. Yet within this perspective of cosmic impermanence lies a strange form of comfort. If everything is temporary, then the suffering and conflicts that dominate human attention represent only brief perturbations in a much larger story. The environmental problems that threaten contemporary civilization, while serious on human timescales, are insignificant compared to the natural changes that Earth will undergo over deep time. Our planet has survived far worse catastrophes than anything humans might inflict, and it will continue to evolve long after our species has either transcended its biological origins or joined the countless others that have vanished into extinction. The Earth of 500 million years hence stands as a monument to the creative power of natural forces operating across timescales that exceed our capacity for intuitive understanding. It is a world that challenges every assumption we hold about the nature of planetary environments, about the possibilities and limitations of life, about the cosmic significance of intelligence and consciousness. In contemplating this alien Earth, we are forced to expand our conception of what planets can become, what life can achieve, and what our own brief existence might mean in the vast context of cosmic evolution. The journey toward this transformed world has already begun. Every second that passes carries Earth deeper into its stellar and planetary future, closer to the alien landscape that awaits at the end of 500 million years of continuous change. The forces that will sculpt that future world are already at work, invisible to casual observation, but relentless in their operation across the deep time that separates us from our planet's ultimate destiny. The transformation begins in the nuclear furnace at the heart of our solar system, where temperatures exceed 15 million degrees Celsius and pressures crush matter beyond terrestrial comprehension. Deep within the Sun's core, hydrogen atoms fuse into helium at a rate of 600 million tons per second, releasing energy that takes 100,000 years to fight its way to the surface before racing across 93 million miles of space to warm our world. But this ancient process, which has remained relatively stable for 4.6 billion years, is entering a phase of inevitable acceleration that will reshape every aspect of Earth's future. The mathematics of stellar evolution are as inexorable as they are terrifying. As helium accumulates in the Sun's core, the nuclear furnace becomes increasingly efficient. The core contracts under its own gravity, driving temperatures and pressures higher, which in turn increases the rate of hydrogen fusion in the surrounding shell. This creates a feedback loop that has been slowly brightening our star throughout its entire main sequence lifetime. What began as a gradual process will accelerate dramatically over the next 500 million years, fundamentally altering the energy balance that has made Earth habitable for billions of years. Current models of stellar physics predict that the Sun's luminosity will increase by approximately 5% over the coming half-billion years. To human intuition, this sounds like a modest change, barely perceptible, perhaps even beneficial for a planet that has experienced ice ages and periods of global cooling. But the reality is far more catastrophic. A 5% increase in solar energy input translates to surface temperature increases of 40 to 50 degrees Celsius in many regions, enough to trigger runaway greenhouse effects that will fundamentally alter the planet's atmospheric chemistry and climate stability. The transformation will not occur uniformly across this vast time span. Stellar evolution models suggest that the brightening will accelerate exponentially, with most of the change concentrated in the final 100 million years of the period we're examining. For the first 400 million years, the changes may be subtle enough that life could potentially adapt through evolutionary mechanisms. But as the Sun approaches the later stages of its main sequence evolution, the rate of change will outpace the ability of biological systems to respond, triggering cascading environmental collapses that will reshape the planet's surface beyond recognition. The increased solar energy will first manifest in disruptions to Earth's delicate climate system. The polar ice caps, which have waxed and waned throughout geological history but have never completely disappeared for extended periods, will melt entirely and permanently. The additional fresh water will alter ocean circulation patterns that have remained stable for millions of years, potentially shutting down the thermohaline circulation that currently distributes heat from the equator toward the poles. Without this global ocean conveyor belt, regional climate patterns will become increasingly extreme. Equatorial regions will experience temperatures that exceed the thermal tolerance of most complex life forms, while areas that currently benefit from warm ocean currents may paradoxically become colder as the global heat distribution system breaks down. These changes will trigger feedback loops that accelerate the overall warming process beyond what solar luminosity alone would produce. The hydrological cycle, which has operated continuously for nearly 4 billion years, will begin to break down under the assault of increased solar radiation. Higher temperatures will drive more vigorous evaporation from the world's oceans, initially creating more intense storm systems and more dramatic weather patterns than anything in recorded history. But the additional water vapor in the atmosphere will act as a greenhouse gas, trapping more heat and driving temperatures even higher in a process that planetary scientists call a runaway greenhouse effect. This process has already occurred on Venus, Earth's sister planet, where surface temperatures now exceed 450 degrees Celsius due to an atmosphere composed primarily of carbon dioxide and water vapor. Venus may represent Earth's ultimate fate as solar luminosity continues to increase beyond the limits that can sustain liquid water on the surface. The comparison is particularly sobering because Venus likely possessed oceans early in its history, losing them to space as the sun grew brighter and surface temperatures exceeded the point where water could remain stable in liquid form. The loss of Earth's hydrosphere will occur through a process called atmospheric escape, where water molecules in the upper atmosphere are broken apart by solar ultraviolet radiation, and the resulting hydrogen atoms are lost to space while oxygen either escapes or reacts with surface rocks. This process operates continuously on all planets with atmospheres, but it accelerates dramatically as stellar radiation intensifies and atmospheric temperatures rise above critical thresholds. Current estimates suggest that Earth's oceans contain approximately 1.37 billion cubic kilometers of water, representing a mass of nearly 1.4 billion tons. The loss of this enormous reservoir will not happen overnight, but over millions of years as the brightening sun drives increasingly vigorous atmospheric escape. The process will accelerate as ocean levels drop and the remaining water becomes more concentrated with salts and other dissolved minerals, eventually reaching saturation points where massive crystallization events deposit thick layers of evaporate minerals across the ocean basins. The geological consequences of oceanic loss extend far beyond simple desiccation. Water plays crucial roles in many geological processes, from the weathering of rocks that helps regulate atmospheric carbon dioxide levels to the lubrication of tectonic plate boundaries that enables continental drift. As water becomes scarce, these processes will operate less efficiently, potentially altering the planet's geological evolution in ways that are difficult to predict but certain to be profound. The loss of water will also affect Earth's magnetic field, which is generated by convection currents in the planet's liquid iron outer core. Water-rich minerals in the mantle help drive the convection processes that maintain this magnetic dynamo, and their desiccation could lead to a weakening or collapse of the magnetic field that protects Earth's atmosphere from solar wind erosion. Without magnetic protection, atmospheric loss will accelerate dramatically, exposing the surface to levels of cosmic radiation that would prove lethal to most forms of life. While stellar evolution drives the overall trajectory of Earth's future climate, other cosmic forces will influence the specific timing and character of these changes. Our solar system orbits the center of the Milky Way galaxy once every 225 million years, passing through regions with different densities of gas, dust, and radiation. Over the 500 million year time span we're considering, Earth will complete more than 2 full galactic orbits, potentially encountering cosmic environments significantly different from those that have prevailed throughout recorded history. During these galactic journeys, our solar system may pass through dense molecular clouds that could affect the Sun's energy output and Earth's atmospheric conditions. These encounters might temporarily increase or decrease the rate of stellar evolution, alter the flux of cosmic radiation reaching Earth's surface, or introduce interstellar material into the outer solar system, where it could be captured by planetary atmospheres. While such events are rare and difficult to predict, they represent another source of environmental variability that could influence Earth's long-term habitability. The possibility of nearby supernovae represents perhaps the most dramatic cosmic threat that Earth might face over deep time. When massive stars exhaust their nuclear fuel, they explode with energies that can briefly outshine entire galaxies, releasing intense bursts of gamma rays and other high-energy radiation. A supernova within 30 light-years of Earth could strip away significant portions of the atmosphere and trigger mass extinction events that would fundamentally alter the trajectory of biological evolution. Statistical analysis suggests that Earth experiences the effects of nearby supernova approximately once every 240 million years on average, meaning that our planet will likely encounter at least 2 such events during the half-billion-year period we're examining. The timing of these cosmic catastrophes relative to the ongoing solar brightening could either accelerate environmental collapse or provide temporary relief by injecting dust and debris into the interstellar medium that reduces the amount of solar radiation reaching Earth's surface. Even without such dramatic cosmic interventions, the gradual evolution of the galaxy itself will alter the cosmic environment in which Earth exists. The ongoing merger between the Milky Way and the Andromeda Galaxy, predicted to begin in approximately 4.5 billion years, will not directly affect Earth during the timeframe we are considering. However, gravitational interactions with other galaxies in the local group could alter the orbits of stars within the Milky Way, potentially moving our solar system into regions with different radiation environments or stellar densities. The expansion of the universe itself will continue to stretch the wavelengths of distant starlight, gradually cooling the cosmic microwave background radiation that permeates all of space. While this process occurs too slowly to significantly affect Earth's energy balance over 500 million years, it represents another manifestation of the cosmic evolution that places all planetary environments within larger contexts of change and transformation. On Earth itself, the solid planet beneath our feet will continue to evolve according to the slow but relentless processes of plate tectonics. The continents will drift thousands of miles from their current positions, colliding and separating in configurations that alter global climate patterns and create new mountain ranges while erasing others. The Pacific Ocean, which has been shrinking for the past 180 million years, will continue to close as the Atlantic and Indian Oceans expand, potentially creating new seaways and eliminating others. Perhaps most dramatically, geological models predict the formation of a new supercontinent sometime within the next 250 million years. This massive landmass, sometimes called Pangaea Proxima or Amasia, depending on the specific configuration, will fundamentally alter global climate patterns by concentrating most of Earth's land surface in one area and disrupting the ocean currents that currently distribute heat around the planet. The formation of supercontinents has occurred several times in Earth's history, most recently with Pangaea approximately 300 million years ago. Each assembly creates extreme continental climate conditions in the interior of the supercontinent, with scorching summers and frigid winters that push the limits of biological tolerance. The lack of coastal moderating influences means that seasonal temperature variations can exceed 100 degrees Celsius in some regions, creating desert conditions more extreme than anything currently found on Earth. Supercontinent formation also affects global volcanism and the release of greenhouse gases from Earth's interior. The assembly process involves massive mountain building episodes that can alter atmospheric composition through enhanced weathering of rocks and the burial of carbon in sedimentary formations. Conversely, the eventual breakup of supercontinents often coincides with periods of intense volcanism that release stored carbon dioxide back into the atmosphere, potentially triggering greenhouse warming that amplifies the effects of increasing solar luminosity. The timing of supercontinent formation relative to stellar evolution creates scenarios that could either accelerate or temporarily moderate Earth's transformation. If the assembly occurs during the period of most rapid solar brightening, the combination of continental climate extremes and increased stellar radiation could create surface conditions hostile to complex life several 100 million years earlier than would occur from solar evolution alone. Alternatively, if supercontinent formation coincides with cosmic events that temporarily reduce solar input, the net effect might be to extend the period during which some regions remain habitable. The deep interior of the Earth will also continue to evolve over these vast timescales, driven by the ongoing decay of radioactive elements that have powered geological activity for billions of years. However, the heat production from radioactive decay has been declining steadily since the planet's formation, and will continue to decrease, potentially leading to reduced volcanic activity, weaker magnetic field generation, and less vigorous plate tectonic processes. As the planet's internal heat engine gradually winds down, the solid iron inner core will continue to grow at the expense of the liquid outer core, eventually reaching a size where the dynamics of magnetic field generation may be fundamentally altered. Some models suggest that Earth's magnetic field could weaken dramatically or even collapse entirely within the next billion years as the core structure evolves beyond the configuration that supports the current geodynamo. The loss of magnetic protection would accelerate atmospheric erosion by solar wind and cosmic radiation, potentially shortening the period during which Earth maintains a substantial atmosphere. Without atmospheric protection, surface conditions would become even more extreme, and the planet would more rapidly approach the airless state that characterizes Mars and other bodies that have lost their protective magnetic shields. These multiple lines of evidence — stellar evolution, galactic dynamics, geological transformation, and planetary interior evolution — converge on a single, inescapable conclusion. Earth is entering a period of accelerating change that will fundamentally alter every aspect of the planetary environment over the next 500 million years. The forces driving this transformation operate on timescales that dwarf human comprehension, but their cumulative effects will be more dramatic than any environmental changes in the planet's recorded history. The Great Acceleration has already begun, invisible to casual observation but detectable by the most sensitive instruments of modern science. Each year, the sun grows imperceptibly brighter. Each decade, the continents drift centimeters closer to their future configurations. Each millennium, the gradual loss of atmospheric water and the slow cooling of the planetary interior advance by increments too small to measure but too consistent to ignore. Standing at the threshold of this transformation, we are witnesses to the opening chapter of Earth's transition from a living world to something alien and unrecognizable. The blue marble that has been home to countless generations of life is embarking on a journey toward conditions that will test the very limits of biological adaptation and potentially drive the story of terrestrial life toward either transcendence or extinction. The first casualties of Earth's stellar transformation will not be the creatures that swim in its waters or the forests that crown its continents, but the waters themselves. The ocean that has cradled life for nearly 4 billion years, the vast blue expanse that has remained liquid through ice ages and greenhouse periods, through asteroid impacts and volcanic catastrophes, will begin its slow journey into the vacuum of space, molecule by molecule, until nothing remains but crystallized salt beds and the haunting memory of waves that once broke against shores that no longer exist. The process begins subtly, invisibly, as the brightening sun drives increasingly vigorous evaporation from the ocean's surface. Initially, this enhanced water cycle will create weather patterns of unprecedented intensity. Hurricanes will develop with wind speeds that exceed anything in recorded history, their energy drawn from surface waters heated beyond current temperature ranges. Monsoon systems will deliver torrential rainfall that exceeds the capacity of river systems to contain, while other regions experience droughts more severe than any in the geological record. But this period of climatic violence represents only the opening movement in a longer symphony of destruction. As atmospheric water vapor concentrations increase, the greenhouse effect will amplify beyond the stabilizing mechanisms that have regulated Earth's climate for eons. Water vapor traps infrared radiation more efficiently than carbon dioxide, creating feedback loops that drive surface temperatures steadily higher, despite any attempts by natural systems to restore equilibrium. The critical threshold lies at approximately 1,400 degrees Kelvin in the upper atmosphere, a temperature at which water molecules begin to dissociate into hydrogen and oxygen atoms under the influence of solar ultraviolet radiation. Once this photodissociation begins in earnest, the hydrogen atoms, being the lightest element in the universe, will escape Earth's gravitational field and stream away into interplanetary space. The heavier oxygen atoms will either follow their hydrogen partners into the void or react with surface rocks, gradually oxidizing the planet's crust in a process that will consume much of the remaining atmospheric oxygen. Current models of atmospheric escape suggest that Earth loses approximately 3 kilograms of hydrogen per second under present conditions, a rate so slow that the complete loss of the oceans would require trillions of years. But as solar luminosity increases and atmospheric temperatures rise above the critical dissociation threshold, this escape rate will accelerate exponentially. What begins as a gentle cosmic breeze will become a rushing torrent that strips away Earth's most precious resource at rates measured in millions of tons per year. The ocean will not disappear uniformly. As water escapes to space, the remaining liquid will become increasingly concentrated with dissolved salts, minerals, and other substances that cannot evaporate at terrestrial temperatures. The process resembles a cosmic distillation apparatus, with pure water vapor rising into the atmosphere while leaving behind increasingly concentrated brines that will eventually reach saturation levels for various dissolved compounds. The first minerals to crystallize will be the most soluble salts, primarily sodium chloride, the common table salt that currently comprises about 3.5% of seawater's mass. As water continues to escape and concentrations increase, vast salt flats will emerge from the retreating ocean basins, covering millions of square kilometers with blindingly white crystal formations that stretch beyond the horizon. These deposits will dwarf the salt formations currently found in places like the Bonneville Salt Flats or the Salar de Uyuni, creating landscapes of crystalline desolation that reflect the harsh light of the brightening sun. Following the precipitation of simple salts, more complex minerals will begin to form as the remaining brine reaches saturation levels for calcium sulfate, magnesium compounds, and other dissolved substances. These evaporate formations will create stratified deposits that record the chemical composition of the dying ocean, preserving in stone the final chapters of Earth's hydrological history. Future geologists from other worlds might study these mineral layers much as we study the evaporate sequences that mark ancient salt lakes and inland seas, reading in their crystal structures the story of a planet's transition from water world to desert. The biological consequences of oceanic loss will unfold in waves of extinction that make the great dying events of the geological past appear modest by comparison. Marine ecosystems, which currently support more than 80% of Earth's biodiversity, will face environmental changes more extreme than any in the 550 million year history of complex life. As salinity levels increase beyond the tolerance of all but the most specialized organisms, entire taxonomic groups will vanish in ecological collapses that cascade through food webs with devastating efficiency. The first organisms to succumb will be the microscopic phytoplankton that form the foundation of marine food chains. These tiny plants, which currently produce more than half of the oxygen in Earth's atmosphere through photosynthesis, cannot survive in the hypersaline conditions that will develop as the ocean contracts. Their disappearance will eliminate the primary food source for zooplankton, which in turn support fish populations, which support larger predators in an interconnected web of dependencies that will unravel as the fundamental energy source disappears. Even before salinity reaches lethal levels, rising ocean temperatures will trigger massive die-offs among temperature-sensitive species. Coral reefs, which currently support approximately 25% of all marine species despite occupying less than 1% of ocean area, will experience bleaching events that make current coral mortality appear insignificant. The symbiotic algae that provide corals with energy through photosynthesis cannot function at the elevated temperatures that will become routine, leading to the collapse of reef ecosystems that have persisted through previous episodes of climate change. As surface waters become too warm to support complex life, some organisms may migrate to greater depths where temperatures remain within tolerable ranges. However, this refuge will prove temporary as the warming penetrates progressively deeper into the ocean column. The deep-sea environments that currently harbour bizarre ecosystems around hydrothermal vents and cold seeps will eventually succumb to temperatures that exceed the thermal limits of even the most heat-tolerant extremophiles. The loss of marine life will have cascading effects on terrestrial ecosystems through the disruption of biogeochemical cycles that have operated for billions of years. The ocean currently serves as a massive reservoir for carbon, nitrogen, phosphorus, and other elements essential for life, absorbing these substances from the atmosphere and redistributing them through biological and geological processes. As marine ecosystems collapse and ocean chemistry shifts toward hypersaline conditions, these global cycles will be disrupted in ways that affect all life on the planet. Perhaps most critically, the dying ocean will lose its capacity to absorb atmospheric carbon dioxide through photosynthesis and chemical weathering processes. Currently, the ocean absorbs approximately 25% of all carbon dioxide released into the atmosphere, helping to moderate the greenhouse effect that would otherwise make Earth uninhabitable. As this carbon sink disappears, atmospheric carbon dioxide concentrations will rise to levels not seen since the planet's earliest history, accelerating the greenhouse warming that drives further water loss in a feedback loop that becomes impossible to break. The atmospheric chemistry changes accompanying oceanic loss will fundamentally alter the composition of Earth's envelope of gases. Water vapor, which currently comprises 1 to 4% of the atmosphere depending on location and season, will initially increase dramatically before escaping to space and leaving behind an atmosphere dominated by carbon dioxide, nitrogen, and trace amounts of other gases. Without water vapor to moderate temperature extremes through latent heat transport, daily temperature variations will become more extreme, with scorching days followed by frigid nights as the atmosphere loses its thermal buffering capacity. The loss of atmospheric water vapor will also affect weather patterns in ways that extend far beyond simple temperature changes. Without moisture to fuel storm systems, wind patterns will be driven primarily by thermal differences between heated and cooled surfaces. Dust storms of unprecedented intensity will scour the increasingly arid landscape, transporting fine particles across continental distances and creating atmospheric conditions hostile to any remaining terrestrial life. Cloud formation, which currently helps regulate Earth's temperature through reflection of solar radiation, will become increasingly rare as atmospheric moisture content declines. The loss of cloud cover will create a positive feedback effect, allowing more solar energy to reach the surface while eliminating one of the planet's primary cooling mechanisms. The brilliant white clouds that currently give Earth its distinctive appearance from space will gradually disappear, leaving behind an atmosphere that appears increasingly transparent and alien. The hydrological cycle that has operated continuously for nearly 4 billion years will break down completely as evaporation outpaces precipitation by ever-widening margins. Rivers will become ephemeral features that flow only during the most intense storm events, before disappearing into the increasingly arid landscape. Lakes will contract into salt-encrusted basins that preserve only the hardiest microorganisms in hypersaline pools that eventually evaporate entirely. Groundwater systems, which currently provide fresh water for much of Earth's terrestrial life, will be depleted as the water table drops below the reach of plant roots and natural springs. The aquifers that have stored water for thousands or millions of years will gradually discharge their contents through evaporation and plant transpiration without receiving replenishment from precipitation. even the deepest groundwater reserves will eventually succumb to the inexorable draw of atmospheric escape. The polar ice caps, which have persisted through previous episodes of greenhouse warming, will melt completely and permanently as global temperatures exceed any previous levels in Earth's history. The vast ice sheets of Antarctica and Greenland, containing enough frozen water to raise global sea levels by more than 70 meters, will become rushing torrents that temporarily delay oceanic contraction, while contributing to the atmospheric water vapor that ultimately escapes to space. As the ice caps disappear, they will eliminate one of Earth's most effective climate-regulating mechanisms. Currently, polar ice reflects approximately 90% of solar radiation back to space, helping to moderate global temperatures through the albedo effect. Dark ocean water and bare rock absorb much more solar energy, accelerating the warming process and driving further ice loss in a feedback loop that rapidly eliminates the planet's frozen water reserves. The disappearance of seasonal snow cover will have similar effects in mountainous and high-latitude regions, eliminating the spring snowmelt that currently provides fresh water for billions of organisms during the growing season. Alpine ecosystems, which depend on snowpack for their water supply, will be among the first terrestrial environments to experience complete ecological collapse as their fundamental water source disappears. Perhaps most poignantly, the great river systems that have carved continents and supported civilizations will dwindle to intermittent streams before disappearing entirely. The Amazon, which currently discharges more water into the Atlantic Ocean than the next 7 largest rivers combined, will become a series of disconnected pools in an increasingly arid basin. The Nile, which has sustained life in northeastern Africa for millions of years, will cease to flow as its sources dry up, and evaporation claims whatever water remains. These changes will not occur uniformly across the planet's surface. Some regions may retain liquid water longer than others due to geographical features, elevation differences, or local climate patterns. Mountain valleys with favourable orientations might trap atmospheric moisture long enough to support isolated ecosystems for extended periods. Underground cavern systems could preserve small bodies of water that escape evaporation for millions of years after surface waters have vanished. But these refugia will represent only temporary delays in the inexorable process of planetary desiccation. As atmospheric water vapor continues to escape to space and solar radiation continues to intensify, even the most protected water sources will eventually succumb to evaporation rates that exceed any possible replenishment. The last pools will shrink to puddles, the puddles to patches of damp soil, and finally even the molecular water bound in clay minerals will be driven off by temperatures that exceed the thermal stability of hydrated compounds. The timeline for complete oceanic loss remains uncertain, with estimates ranging from 100 million to more than 1 billion years depending on the rate of stellar brightening and the efficiency of atmospheric escape processes. However, the biological effects will begin much sooner, as rising salinity and temperature levels exceed the tolerance of marine organisms long before the physical disappearance of liquid water from Earth's surface. By the time we reach the 500 million year mark that represents our temporal destination, the ocean may still exist in some form, but it will be fundamentally transformed beyond recognition. What remains will be hypersaline pools scattered across ancient basin floors, supporting only the most specialized microorganisms adapted to extreme conditions. The vast blue expanse that has defined Earth's appearance for eons will have contracted to a series of isolated brine lakes, surrounded by endless salt flats that stretch toward horizons shimmering with heat. Standing at the shore of this dying ocean, watching the last waves lap against crystalline beaches where no life stirs beneath the harsh light of an alien sun, we confront the ultimate impermanence of the world we know. The water that gave birth to life, that has shaped continents and moderated climates, that has reflected countless sunsets and supported the dreams of every creature that has ever gazed upon its surface, will have begun its final journey into the cosmic void, leaving behind only memories crystallized in salt and stone. Life has survived every catastrophe that Earth has thrown at it across 3.8 billion years of evolutionary history. It has endured the oxygen holocaust that poisoned early anaerobic organisms, weathered the snowball Earth episodes that encased the planet in kilometre-thick ice, and recovered from asteroid impacts that vaporized entire ecosystems. But the challenges awaiting life over the next 500 million years will test the very limits of biological adaptability. forcing evolution to explore radical solutions that push organisms beyond the boundaries of anything we recognize as life today. The first responses will emerge from the microscopic realm, where organisms already exist at the extremes of biological possibility. Deep beneath the ocean floor, in volcanic vents where temperatures approach the boiling point of water, communities of thermophilic bacteria currently thrive in conditions that would instantly kill most surface life. These extremophils represent evolutionary experiments that have been running for billions of years, preparing life for challenges more severe than any the surface world has ever faced. As ocean temperatures rise beyond the tolerance of conventional marine organisms, these heat-loving microbes will inherit vast new territories. Hydrothermal vent ecosystems, currently confined to isolated points along mid-ocean ridges, will expand across entire ocean basins as rising global temperatures create conditions suitable for thermophilic life throughout the water column. Bacteria capable of surviving at 120 degrees Celsius will find themselves in a world where such temperatures become commonplace rather than exceptional. But even these hardy organisms face limits. The current record holder for heat tolerance, strain 121, can survive temperatures up to 121 degrees Celsius under laboratory conditions, but most thermophiles operate optimally at lower temperatures and struggle to maintain cellular integrity as thermal stress increases. As Earth's surface temperatures climb toward 200 degrees Celsius and beyond, even the most heat-adapted organisms will be forced to either evolve unprecedented thermal tolerance or retreat to increasingly marginal environments. The evolutionary pressure will drive organisms toward biochemical innovations that challenge our understanding of life's fundamental requirements. Proteins, the molecular machines that drive all biological processes, begin to denature and lose functionality at temperatures above 100 degrees Celsius. But some organisms have already developed heat shock proteins and other stabilizing molecules that protect cellular machinery from thermal damage. The evolutionary descendants of these creatures might develop entirely new classes of heat-resistant biomolecules, perhaps based on silicon chemistry, rather than the carbon-based biochemistry that dominates current life. Silicon-based life has long been a staple of science fiction, but the chemical properties of silicon make it a poor substitute for carbon under normal conditions. However, at the extreme temperatures that will characterize Earth's future, silicon compounds might provide advantages over their carbon-based equivalents. Silicon-oxygen bonds remain stable at much higher temperatures than carbon-hydrogen bonds, potentially allowing organisms to maintain complex molecular structures under conditions that would destroy conventional organic compounds. The transition from carbon-based to silicon-based biochemistry would represent one of the most fundamental evolutionary innovations in Earth's history, comparable to the development of photosynthesis or the evolution of complex cells. Such organisms would be as alien to current life as modern plants are to the earliest anaerobic bacteria, yet they might represent life's only path to survival in a world where traditional biochemistry becomes impossible. As surface waters become too salty and hot to support conventional aquatic life, evolutionary pressure will drive organisms toward terrestrial environments that might provide temporary refuge from the worst extremes. But the land will face its own challenges as the hydrological cycle breaks down and atmospheric conditions become increasingly hostile. Plants, which currently depend on liquid water for photosynthesis and nutrient transport, will need to develop radically new strategies for survival in a world where water becomes increasingly scarce and temperatures exceed the operating limits of existing cellular machinery. Some organisms might evolve toward complete independence from liquid water, deriving moisture from atmospheric humidity or from biochemical processes that generate water as a metabolic byproduct. Desert-adapted plants already demonstrate remarkable water conservation strategies, with some cacti capable of surviving entirely on water absorbed from morning dew. The evolutionary descendants of such organisms might develop even more extreme water-saving adaptations, perhaps storing water in specialized cellular compartments that remain liquid at temperatures well above 100 degrees Celsius through the use of antifreeze proteins or high-pressure cellular environments. Alternatively, plants might abandon traditional photosynthesis entirely in favor of chemosynthetic processes that derive energy from chemical reactions rather than sunlight. Deep-sea vent communities already demonstrate the viability of chemosynthetic ecosystems, with bacteria converting hydrogen sulfide and other chemicals into usable energy. As Earth's surface becomes increasingly rich in reactive chemicals released from volcanic activity and rock weathering, chemosynthetic organisms might find abundant energy sources that allow them to thrive without depending on the solar radiation that drives traditional photosynthesis. The most radical evolutionary response might involve the abandonment of surface environments, entirely in favour of deep subsurface habitats that remain insulated from the worst extremes of climate change. The deep biosphere, which extends several kilometres beneath Earth's surface, currently hosts communities of organisms that derive energy from radioactive decay, chemical weathering, and other processes completely independent of surface conditions. These deep subsurface ecosystems might represent the last refuge for complex life, as surface conditions become increasingly hostile. Miles beneath the surface, temperatures remain relatively stable. Water remains liquid in microscopic pore spaces, and chemical energy sources continue to operate regardless of what happens to the atmosphere above. Organisms that successfully colonize these environments might survive long after surface life has been eliminated, evolving in isolation for millions of years, while the planet above them transforms into an alien desert. The evolutionary journey into deep subsurface environments would require organisms to develop unprecedented adaptations for life under extreme pressure, in complete darkness, and with minimal energy resources. Current deep subsurface organisms grow extraordinarily slowly, with some bacteria taking thousands of years to reproduce. But evolutionary pressure might drive the development of more efficient metabolisms that allow faster growth and more complex ecological relationships in these extreme environments. Some organisms might even evolve mechanisms for surviving in a dormant state for millions of years, waiting out the worst periods of planetary transformation before emerging to recolonize surface environments if conditions ever become favorable again. Bacterial spores can already survive for thousands or even millions of years in harsh conditions, and some organisms have been revived from ancient salt deposits and permafrost layers that preserved them across geological timescales. The most speculative but potentially revolutionary evolutionary path involves the development of organisms capable of surviving in the vacuum of space itself. While this might sound impossible, some Earth organisms already demonstrate remarkable resistance to space conditions. Tardigrades, microscopic animals commonly known as water bears, can survive exposure to the vacuum of space for extended periods, entering a dormant state that protects them from radiation, temperature extremes, and the absence of atmospheric pressure. If organisms could evolve enhanced space survival capabilities, they might be able to escape Earth's increasingly hostile environment entirely, dispersing to other worlds where conditions remain suitable for life. Such organisms might hitch rides on asteroids or comets ejected from Earth by massive impacts, spreading terrestrial life throughout the solar system in a process called panspermia. The development of spacefaring organisms would represent the ultimate evolutionary escape from planetary limitations, allowing life to transcend the boundaries that have confined it to a single world throughout its entire history. Such organisms might colonize Mars, the moons of Jupiter and Saturn, or even interstellar space itself, carrying the genetic legacy of Earth life to environments we cannot imagine. But perhaps the most intriguing evolutionary possibility involves the development of technological capabilities within biological organisms themselves. Current life forms already demonstrate remarkable nanotechnology, with cellular machinery that operates at the molecular level to repair damage, construct complex structures, and process information. The evolutionary descendants of intelligent species might develop biological technologies that allow them to manipulate their environment in ways that ensure survival under extreme conditions. Such biotechnological organisms might be capable of engineering their own genetics in real time, adapting their biochemistry to changing environmental conditions within their own lifetimes, rather than waiting for evolutionary processes to operate across generations. They might develop biological systems for manufacturing protective shelters, processing scarce resources, or even modifying local environmental conditions to create habitable microclimates. The ultimate expression of this evolutionary path might be the development of organisms that exist primarily as information, rather than physical matter, storing their genetic and cultural heritage in forms that can survive the complete destruction of their biological substrates. Such digital organisms might preserve the essence of life in crystalline matrices, quantum storage systems, or other information preservation mechanisms that remain stable across geological timescales. intelligence itself might evolve beyond its current biological constraints, developing forms of consciousness that can operate in environments hostile to conventional life. If intelligence can be divorced from its biological substrate and implemented in more durable physical systems, it might survive planetary catastrophes that would eliminate all biological organisms. The question of whether intelligence represents life's ultimate survival strategy becomes particularly acute when we consider the timeframes involved in Earth's future transformation. Individual organisms might evolve remarkable adaptations for surviving extreme conditions, but intelligence potentially offers something even more powerful: the ability to actively modify environmental conditions rather than simply adapting to them. Intelligent species might develop technologies for managing planetary climate, maintaining habitable conditions through artificial means long after natural processes would render the planet uninhabitable. They might construct underground cities that provide controlled environments for biological life, or develop space-based habitats that allow entire ecosystems to survive the eventual destruction of Earth's surface. The development of such technologies would require intelligence to persist across the millions of years necessary for their development and implementation. This represents perhaps the greatest challenge facing any potential intelligent descendants of current Earth life, since technological civilizations have historically proven vulnerable to collapse long before they develop the capabilities necessary for planetary-scale environmental management. Yet the prospect of intelligence transcending planetary limitations offers the most hopeful scenario for life's long-term survival. If consciousness can develop forms that are not dependent on biological substrates, and if intelligent beings can develop technologies that allow them to modify planetary environments or migrate to more favorable worlds, then the story of Earth life need not end with the planet's transformation into a sterile desert. The evolutionary responses to Earth's future challenges might produce forms of life so radically different from current organisms that we would struggle to recognize them as living at all. Silicon-based biochemistries, digital consciousness, space-adapted organisms, and biotechnological hybrids represent possibilities that stretch the definition of life to its breaking point. Yet all of these speculative evolutionary paths share a common thread. They represent attempts by life to transcend the limitations that have constrained it throughout its history. The upcoming environmental challenges will force evolution to explore territories that have never been tested, pushing the boundaries of what we consider possible for biological systems. Some of these evolutionary experiments will undoubtedly fail, leading to extinction events that eliminate entire branches of the tree of life. But others might succeed in ways that transform our understanding of life's possibilities, creating new forms of existence that can thrive under conditions that would be lethal to every organism currently living on Earth. The next 500 million years will serve as the ultimate test of life's adaptability, creativity, and resilience. The organisms that emerge from this crucible of environmental extremes might bear little resemblance to anything we recognize today, but they will carry forward the genetic and cultural legacy of billions of years of evolutionary innovation. Whether life ultimately succeeds in transcending Earth's limitations or succumbs to environmental challenges beyond its adaptive capacity, the attempt itself represents one of the most remarkable experiments in the history of the universe, the struggle of matter and energy organized into living systems to persist and evolve in the face of cosmic forces that care nothing for their survival. The evolutionary exodus that begins with Earth's environmental transformation might end with life itself transcending the planetary boundaries that have defined its existence for nearly 4 billion years, carrying the spark of consciousness and complexity into realms we cannot yet imagine. Or it might end in silence, with the last organisms succumbing to conditions beyond their capacity to endure, leaving behind only the chemical traces of their existence in rocks that will themselves eventually be recycled by geological processes. In either case, the journey represents the ultimate expression of life's fundamental drive to persist, adapt, and evolve in the face of challenges that would seem insurmountable to any individual organism, but which become opportunities for evolutionary innovation when approached with the creativity and persistence that has characterized life throughout its remarkable history on this dynamic planet. In the deep laboratories of evolutionary possibility, where chance mutations collide with environmental pressures across millions of generations, alternative futures for Earth life branch like the limbs of an infinite tree. Each pathway represents a world that might emerge from the crucible of planetary transformation, some familiar enough to recognize as descendants of current life, others so alien that they challenge our fundamental assumptions about what living systems can become. The first alternative future unfolds in the shallow seas that persist long after the great oceans have contracted into hypersaline pools. Here, in waters 10 times saltier than today's Dead Sea, evolution experiments with organisms that have abandoned the cellular architectures that have dominated life for billions of years. These halophilic descendants of ancient archaea have developed crystalline structures within their cell walls, living lattices of salt and protein that maintain structural integrity under extreme salinity conditions, while harvesting energy directly from the mineral gradients that surround them. These crystal-based organisms represent life's solution to a world where traditional biochemistry fails. Their cellular machinery operates through quantum tunneling effects in their crystalline matrices, processing information and energy at the molecular level through mechanisms that blur the line between biology and geology. Colonies of these creatures create vast living reefs of organized salt crystals, their surfaces shimmering with bioluminescent displays that communicate across kilometers of hostile water through patterns of light that encode complex chemical and genetic information. The terrestrial equivalent of this crystalline evolution takes root in the endless salt flats that mark the graves of vanished oceans. Here, organisms have evolved that exist primarily as mineral structures, animated by quantum processes, their consciousness distributed through networks of organized crystals that span continents. These lithophytic beings derive energy from radioactive decay in the rocks beneath their feet, processing information through quantum entanglement between distant parts of their continental-scale bodies. To human eyes, these landscapes would appear utterly lifeless, endless expanses of white crystal formations that stretch beyond the horizon under the harsh light of an aging sun. But beneath this sterile surface, a form of consciousness operates that experiences existence on geological timescales, thinking thoughts that require centuries to complete and implementing decisions across millions of years of patient crystalline growth. In the deep atmosphere of this transformed Earth, where temperatures at altitude remain cool enough to support complex chemistry, another branch of evolution explores the possibilities of thus-aerial life. The descendants of microorganisms that once drifted in cloud droplets have evolved into vast networks of atmospheric organisms, living systems that exist entirely as organized patterns of chemical reactions suspended in the thin air above the scorching surface. These atmospheric beings have no physical bodies in any conventional sense. They exist as self-organizing chemical cascades that maintain their structure through constant interaction with the mineral-rich dust storms that sweep across the planet's surface. Their reproduction involves the fragmentation of successful chemical patterns that then seed new atmospheric regions with copies of their reactive networks. From the surface, these aerial organisms might be visible as strange aurora-like displays that dance across the sky in patterns too complex to be purely physical phenomena. They communicate through modulated electromagnetic fields that create interference patterns in radio wavelengths, potentially broadcasting their thoughts across interplanetary distances to similar organisms that might have evolved in the atmospheres of other worlds. Perhaps the most radical evolutionary experiment unfolds in the planet's deep subsurface, where the descendants of extremophil bacteria have developed collective intelligences that operate through biofilms spanning thousands of cubic kilometers of rock. These underground minds process information through chemical signals that propagate through interconnected pore spaces at the speed of molecular diffusion, creating thought processes that operate over timeframes measured in millennia. Individual cells within these massive neural networks might live and die thousands of times during the completion of a single thought, but the collective intelligence persists across geological ages, accumulating knowledge and making decisions that affect the planet's long-term geological evolution. These subsurface minds might actively manage the chemistry of groundwater systems, the stability of rock formations, and even the planet's seismic activity through biochemical processes that influence large-scale geological phenomena. The most unsettling possibility is that such underground intelligences already exist, thinking thoughts so slow and alien that we have never recognized their presence. The strange patterns of mineral distribution in some rock formations, the unexplained correlations in seismic activity across distant regions, the mysterious chemical signatures in deep groundwater, all of these might represent the fingerprints of minds operating on scales and timeframes that dwarf human comprehension. In the scorching surface regions where temperatures approach those of Venus, evolution might produce organisms based entirely on plasma chemistry rather than conventional molecular biology. These high-energy beings would exist as organized patterns of charged particles, maintaining their structure through electromagnetic fields while deriving energy from the intense solar radiation that makes their environment uninhabitable to conventional life. Such plasma-based organisms might resemble miniature lightning storms, their bodies composed of flowing electrical currents that dance across the superheated landscape in patterns too complex to be purely physical phenomena. They would reproduce through electromagnetic induction, creating copies of their electrical patterns in suitable plasma environments, and might achieve forms of collective intelligence through synchronized electromagnetic oscillations that span entire continents. The descendants of these plasma beings might eventually develop the ability to exist in the vacuum of space itself, their electromagnetic bodies no longer requiring any material substrate. Such organisms could survive the eventual boiling away of Earth's atmosphere and the expansion of the Sun into a red giant, persisting as pure information encoded in electromagnetic field patterns that propagate through interstellar space at the speed of light. But the most intriguing evolutionary pathway involves the potential emergence of technological organisms, beings that develop the ability to design and construct artificial environments that allow them to transcend the limitations of their biological heritage. The descendants of current intelligent species might achieve a symbiotic relationship with their technology, evolving biological systems that interface directly with artificial devices to create hybrid organisms that combine the adaptability of life with the precision and durability of engineered systems. These biotechnological beings might inhabit vast underground cities carved from solid rock, their living quarters sealed against the hostile surface environment, while their biological systems interface with mechanical life support systems that maintain optimal conditions for survival. Their bodies might incorporate both evolved organs and engineered components, with artificial lungs that can process the chemical atmospheres of different planetary environments, and synthetic neural interfaces that allow direct communication with the artificial intelligences that manage their technological infrastructure. The ultimate expression of this evolutionary pathway might be the development of organisms that exist primarily as software running on biological hardware, conscious beings whose minds can be transferred between different physical substrates as environmental conditions change. Such digital organisms might survive the destruction of their original bodies by uploading their consciousness into crystalline storage matrices or quantum computational systems that remain stable across geological timescales. These uploaded minds might then construct new physical bodies adapted to whatever environmental conditions exist, downloading their consciousness into biological or mechanical systems designed for specific purposes. They might exist simultaneously in multiple bodies distributed across different environments, their consciousness divided among underground refuges, atmospheric platforms, deep-sea installations, and space-based habitats. The possibilities become even more extraordinary when we consider the potential for conscious organisms to directly manipulate their own evolutionary processes through advanced genetic engineering technologies. Rather than waiting for natural selection to operate across millions of years, these self-modifying beings might redesign their biological systems in real time to adapt to rapidly changing environmental conditions. Such organisms might maintain genetic libraries containing the blueprints for thousands of different body configurations, each optimized for specific environmental conditions. As planetary conditions change, they could literally rebuild themselves from the cellular level up, transforming from aquatic to terrestrial to aerial forms as needed, or even splitting their consciousness among multiple specialized bodies simultaneously. The descendants of Earth's current ecosystem might include species that spend part of their life cycle as deep-sea organisms adapted to the hypersaline pools that remain of the ancient oceans, then metamorphose into atmospheric forms that exist in the planet's upper atmosphere, and finally transform into crystalline entities that survive in the mineral deposits of the deep subsurface. Each life stage might last for millions of years, with individual organisms experiencing the full range of Earth's transformed environments across their extended lifespans. Perhaps most remarkably, some evolutionary pathways might lead to organisms that actively engineer planetary environments to suit their needs, rather than simply adapting to existing conditions. These environmental architects might develop technologies for managing atmospheric composition, regulating surface temperatures, and maintaining stable chemical conditions across geological timescales. Such organisms might construct vast atmospheric processes that convert the planet's increasingly hostile atmosphere into breathable mixtures for biological life. They might build orbital mirrors that reflect excess solar radiation away from the planet's surface, or develop deep drilling technologies that tap the planet's internal heat sources to provide energy for civilization-scale environmental management systems. The most ambitious environmental engineering projects might involve the construction of artificial worlds, space-based habitats that provide optimal conditions for biological life while remaining independent of planetary environmental conditions. These artificial ecosystems might preserve the genetic and cultural heritage of Earth life long after the planet itself becomes uninhabitable, serving as arcs that carry terrestrial organisms to other star systems where they might establish new biospheres. But even these remarkable technological achievements pale before the possibility that consciousness itself might evolve beyond any dependence on material substrates. Advanced intelligences might discover ways to encode their thoughts and memories in the fundamental structure of space-time itself, achieving a form of existence that persists regardless of what happens to planets, stars, or even galaxies. Such transcendent beings might experience existence as pure information, their consciousness distributed through quantum fields that span cosmic distances. They would be immune to planetary catastrophes, stellar evolution, and even the heat death of the universe, persisting as patterns of organized information that maintain their structure through mechanisms we cannot currently comprehend. The transformation of matter into consciousness represents the ultimate evolutionary achievement, the conversion of the universe itself into a living system capable of thought, experience, and creative action. In this scenario, the death of Earth would represent not the end of terrestrial life, but its graduation to a higher form of existence that transcends all physical limitations. Yet for every pathway toward transcendence, evolution might also explore dead ends that lead to beautiful but ultimately doomed experiments in biological possibility. Some organisms might develop exquisite adaptations to environmental conditions that prove temporary, creating evolutionary masterpieces that flourish briefly before succumbing to further environmental changes. The crystal gardens of the hypersaline seas might achieve breathtaking complexity before the last pools evaporate entirely. The atmospheric intelligences might compose symphonies of electromagnetic beauty that echo through the thin air before the planet's magnetic field collapses and strips away the remaining atmosphere. The deep subsurface mines might achieve profound insights about the nature of geological time before the planet's interior finally cools beyond their operational temperature range. These failed experiments would not represent evolutionary mistakes, but rather explorations of possibilities that enrich the universe, even if they cannot persist indefinitely. The patterns of organization they achieve, the forms of beauty they create, and the types of consciousness they develop might influence the evolution of life on other worlds, or inspire artificial intelligences that encounter their fossilized remains millions of years in the future. The branching pathways of Earth's evolutionary future create a vast space of possibility that includes everything from silicon-based crystalline networks to quantum-coherent plasma entities to uploaded digital consciousnesses that exist as pure information. Each pathway represents a different answer to the fundamental question of how organized matter can persist and evolve in the face of environmental challenges that exceed anything in the planet's history. Some of these futures might seem more plausible than others based on our current understanding of biology, physics, and chemistry. But the history of life on Earth is filled with evolutionary innovations that would have seemed impossible before they actually occurred. The development of photosynthesis, the evolution of complex cells, the emergence of multicellular organisms, and the appearance of consciousness all represented unprecedented breakthroughs that transformed the possibilities for future evolution. The environmental challenges facing Earth over the next 500 million years will drive evolution toward equally unprecedented innovations, potentially producing forms of life and consciousness that expand our conception of what organized matter can achieve. Whether these evolutionary experiments succeed or fail, they will represent some of the most remarkable explorations of possibility in the history of the universe. Standing at the threshold of these branching futures, we can only imagine the strange worlds that might emerge from the intersection of evolutionary creativity and environmental extremity. Each possibility represents a different vision of what Earth might become when the familiar blue planet of our experience transforms into something utterly alien yet still, in some fundamental sense, alive. The silence is the first thing that strikes any observer who might witness Earth's final centuries of habitability. Where once the planet hummed with the constant symphony of wind through forests, waves against shores, and the calls of countless creatures across land and sea, now only the whisper of superheated air remains, carrying dust storms across landscapes that have been scoured clean of every trace of the biological abundance that once defined this world. The sun hangs in a sky that has become the colour of molten copper, its disk visibly larger than it appeared to the last humans who walked this surface hundreds of millions of years ago. The stellar evolution that began as an imperceptible brightening has reached its crescendo within the main sequence phase, pushing Earth past the final threshold of planetary habitability. The additional 5% of solar energy that seemed modest when considered as a mere percentage has transformed into a death sentence for any form of life that requires stable temperatures, liquid water, or atmospheric conditions that bear any resemblance to those that supported the evolution of complex organisms. Surface temperatures now routinely exceed 80 degrees Celsius in the planet's polar regions, while equatorial zones experience thermal conditions that approach 120 degrees Celsius during the peak heating of each day. These are temperatures that denature proteins, break apart the molecular machinery of cellular life, and reduce organic compounds to their constituent elements. The biochemistry that powered 4 billion years of evolutionary innovation has been rendered impossible by the relentless assault of thermal energy that bathes every square metre of Earth's surface. The atmosphere itself has become an alien mixture that would be toxic to any organism from Earth's biological past. The last traces of water vapour escaped to space more than 50 million years ago, taking with them the final vestiges of the hydrological cycle that once moderated planetary temperatures and distributed life-giving moisture across continents and ocean basins. What remains is a thin envelope of carbon dioxide, nitrogen, and trace gases that provides no cooling effect and offers no protection from the increasingly harsh solar radiation that penetrates to the surface with intensities that would have been lethal to life even during the most extreme greenhouse periods of the geological past. The landscapes that stretch beneath this hostile sky bear no resemblance to anything that existed during the planet's habitable epochs. The continents have been sculpted by wind erosion of unprecedented intensity, their surfaces ground down to bedrock by dust storms that operate continuously in the absence of any vegetation or moisture to bind soil particles together. Mountain ranges that took hundreds of millions of years to form through tectonic processes have been reduced to rounded hills and scattered boulder fields, their peaks worn away by the ceaseless abrasion of mineral particles carried on superheated winds. Where ancient ocean basins once held vast bodies of water that teemed with life, now only crystalline plains extend toward horizons that shimmer with heat mirages. The evaporate deposits left behind by the dying seas have been organised by wind and thermal cycling into geometric patterns that create landscapes of surreal beauty, endless expanses of white and coloured mineral formations that arrange themselves in polygonal networks resembling the surface features of Mars or the dried lake beds of the most arid regions that existed during Earth's transition period. These salt flats preserve in their layered deposits the final chemical signature of Earth's hydrosphere, with each stratum recording the progressive concentration of dissolved minerals as the oceans contracted and eventually disappeared entirely. The deepest layers contain the remains of the last marine organisms, microscopic shells and cellular fragments that mark the final chapter in the story of aquatic life that began nearly 4 billion years earlier in the warm pools of Archean seas. The geological processes that shaped Earth throughout its history continue to operate, but they have been fundamentally altered by the absence of water and the extreme thermal conditions that now prevail. Plate tectonics proceeds at a dramatically reduced pace, as the lubricating effects of water in the mantle decrease and the increasing rigidity of superheated surface rocks resist the stresses that drive continental motion. The planet's internal heat engine still functions, but its surface expression through volcanism and mountain building has become less efficient and more sporadic. Volcanic eruptions, when they occur, create scenes of almost supernatural intensity as molten rock encounters atmospheric and surface conditions unlike any in the planet's previous history. The lava flows that emerge from these eruptions cool more slowly in the thin, superheated atmosphere, creating extensive basaltic plains that cover thousands of square kilometers with smooth, dark surfaces that absorb solar radiation with devastating efficiency and radiate heat back to the atmosphere in patterns that drive the massive dust storms that continuously reshape the planet's topography. The magnetic field that once protected Earth's atmosphere from solar wind erosion has weakened dramatically as the planet's core structure evolved beyond the optimal configuration for magnetic dynamo generation. Without this electromagnetic shield, the solar wind strips away atmospheric particles at accelerated rates, gradually thinning the envelope of gases that surrounds the planet and exposing the surface to increasingly intense cosmic radiation that would prove lethal to any biological organism within minutes of exposure. Yet in the deepest reaches of the planetary subsurface, in caverns and cracks that extend more than 10 kilometers beneath the hostile surface, the final communities of Earth life persist in conditions that push the very boundaries of biological possibility. These are the ultimate extremophiles, descendants of organisms that have been adapting to increasingly harsh conditions for hundreds of millions of years as surface environments gradually became uninhabitable. The dominant life forms in these deep refugia bear no resemblance to any organisms that existed during Earth's surface-dwelling biological epochs. They derive energy not from photosynthesis or the consumption of other organisms, but from the chemical gradients created by radioactive decay, serpentinization reactions, and the slow weathering of minerals in the absence of liquid water. Their metabolisms operate at temperatures that would have been instantly fatal to their evolutionary ancestors, and they have developed cellular mechanisms that function efficiently in environments where traditional biochemistry becomes impossible. These deep subsurface ecosystems exist in near-complete isolation from surface conditions, insulated by kilometers of rock that maintain stable temperatures regardless of the thermal chaos occurring above. Here, in networks of interconnected fractures and cave systems, communities of thermophilic bacteria and archaea have established the planet's final biosphere, a shadow of the rich ecological networks that once flourished in surface oceans and terrestrial environments, but representing life's ultimate adaptation to conditions that approach the absolute limits of biological tolerance. The organisms that comprise these terminal ecosystems have evolved beyond recognition as life in any conventional sense. Some exist as living mineral matrices that blur the distinction between biology and geology, their cellular structures reinforced with crystalline frameworks that maintain integrity under extreme pressure and temperature conditions. Others have developed dormancy mechanisms that allow them to survive in cryptobiotic states for millions of years, waiting out periods when local conditions exceed even their remarkable tolerances. Perhaps most remarkably, some of these deep-dwelling organisms have evolved collective behaviors that operate across geological timescales. Networks of interconnected microorganisms communicate through chemical signals that propagate through groundwater systems at rates measured in centuries, coordinating resource utilization and environmental management across continental-scale distances. These living systems actively modify their local chemical environments, maintaining conditions suitable for their survival through biogeochemical processes that influence everything from local pH levels to the availability of essential nutrients. The energy sources that sustain these final communities are themselves finite. The radioactive elements that have powered Earth's geological activity for billions of years continue to decay at predictable rates, gradually reducing the heat flow from the planet's interior that drives many of the chemical reactions upon which deep subsurface life depends. The serpentinization processes that generate hydrogen gas from the interaction of water with certain types of rock operate more slowly as groundwater reserves are depleted, and mineral substrates are exhausted through billions of years of continuous reaction. As these energy sources diminish, the deep subsurface ecosystems face their own ultimate extinction timeline. The communities that represent life's final stand against planetary inhospitability are themselves engaged in a gradual retreat into ever smaller refugia as the chemical and thermal conditions that support their existence continue to deteriorate. Some organisms respond by entering extended dormancy states, reducing their metabolic activity to levels so low that they approach the boundary between life and death. The question that haunts these final epochs of terrestrial biology is whether any form of information, genetic, cultural or otherwise, can survive the complete sterilization of the planet that appears inevitable within the next 100 million years. Some of the most sophisticated deep subsurface organisms have evolved mechanisms for encoding information in crystalline structures that remain stable across geological timescales, potentially preserving records of Earth's biological history in forms that could survive the planet's transformation into a completely sterile world. These biological archives might contain the genetic sequences of long-extinct organisms, compressed records of evolutionary histories that span billions of years, or even more abstract forms of information that encode the experiences and adaptations of entire ecosystems. The discovery and interpretation of such archives by hypothetical future visitors to the lifeless Earth might provide insights into biological processes and evolutionary innovations that would otherwise be lost forever when the last organisms succumb to conditions beyond their capacity to endure. But the preservation of information represents only a pale reflection of the rich, dynamic complexity that characterized Earth's biosphere during its billions of years of active evolution. The interactive networks of organisms that created and maintained the environmental conditions necessary for continued biological innovation will be eliminated long before the planet's final sterilization, leaving behind only static records of what once was rather than the living systems capable of continued adaptation and evolution. The collapse of these final biological communities occurs not through dramatic extinction events like those that punctuated Earth's earlier history, but through the gradual exhaustion of the energy sources and environmental conditions that make life possible. Individual organisms may persist for thousands or even millions of years after their reproductive capacity has been eliminated by environmental stress, creating populations of living fossils that represent evolutionary endpoints rather than stages in ongoing adaptation. As the deep subsurface refugia contract and their energy sources dwindle, the planet approaches a state that has not existed since the earliest Archean eon, more than 3 billion years ago. A world where geological and chemical processes proceed in the absence of any biological influence. The biogeochemical cycles that have operated for eons, the movement of carbon, nitrogen, sulfur and other elements through living systems, will cease entirely, leaving only the purely physical and chemical processes that operate according to thermodynamic principles, rather than the complex feedback mechanisms that characterize living systems. The approach of this biological endpoint represents more than simply the death of Earth's last organisms. It marks the termination of the most remarkable experiment in the history of the solar system, the development of matter into self-organizing, self-replicating systems capable of evolution, consciousness, and the manipulation of their environment on planetary scales. The information processing capabilities that allowed living systems to respond to environmental challenges with creative adaptations will be eliminated, leaving behind a world governed entirely by the mechanical operation of physical laws. Yet even as the final organisms struggle for survival in their deep Earth refugia, the planet continues its inexorable journey through the cosmic processes that will ultimately determine its fate. The Sun's evolution toward ever greater luminosity proceeds according to the mathematical certainties of stellar physics, promising even more extreme conditions in the geological future that lies ahead. The tectonic processes that have shaped continents and ocean basins for billions of years continue to operate, albeit at reduced intensity, carrying the planet toward new configurations that will further alter surface and atmospheric conditions. The magnetic field continues its gradual weakening as the core structure evolves beyond the parameters that support strong magnetic dynamo activity. Atmospheric loss to space accelerates as solar wind erosion encounters decreasing resistance from the planet's electromagnetic defenses. The thin atmosphere that remains becomes progressively less capable of moderating temperature extremes or protecting the surface from cosmic radiation, hastening the sterilization process that eliminates the last traces of biological activity. Standing at this threshold between a biologically active planet and a sterile world, we witness the culmination of processes that have been operating since Earth's formation more than 4 billion years ago. The gradual evolution of stellar luminosity, the slow cooling of planetary interiors, the progressive loss of atmospheric constituents to space, all of these processes have been pushing Earth toward this moment when the conditions that made life possible finally exceed the adaptive capacity of even the most resilient organisms. The transition represents not merely the end of life on Earth, but the closing of a unique chapter in cosmic history. Among the countless planets that orbit stars throughout the galaxy, the subset that develops and maintains conditions suitable for the emergence of complex evolving biological systems appears to be vanishingly small. Earth's 4 billion year experiment in biological innovation, consciousness development, and ecosystem complexity may represent a phenomenon so rare that its termination eliminates possibilities that will never again be replicated in this corner of the universe. The final threshold has been crossed. The planet that gave birth to life, nurtured its evolution through countless environmental crises, and supported the development of consciousness capable of contemplating its own existence, approaches the moment when it will join the vast majority of worlds that exist as sterile collections of rock, metal, and atmosphere operating according to purely physical principles. The silence that characterizes Earth's final habitable centuries will soon become permanent, broken only by the sound of wind carrying dust across landscapes that will never again know the footsteps of any living creature. In this approaching silence lies both tragedy and a strange form of peace. The struggles that have driven evolutionary innovation for billions of years will finally end, replaced by the mathematical certainty of thermodynamic processes that operate without consciousness, without purpose, and without the creative chaos that characterizes living systems. Earth will have completed its transformation from a world of infinite biological possibility into a monument to the ultimate impermanence of even the most successful experiments in cosmic organization. The final threshold marks not just the end of Earth's biological story, but the beginning of its purely geological future, a future that will unfold across timescales that dwarf even the vast spans we have contemplated as the planet continues its journey through stellar evolution, galactic motion, and the larger cosmic processes that shape the destiny of matter and energy throughout the universe. We stand now at the end of our journey through deep time, having witnessed the transformation of Earth from the blue marble of our experience into a sterile monument to the impermanence of all things. 500 million years stretch behind us, like a vast canyon of transformed possibilities, each geological epoch representing changes more profound than our minds were evolved to comprehend. Yet in completing this temporal voyage, we have not merely observed the death of a world, we have participated in one of the most fundamental exercises available to conscious beings, the contemplation of our own cosmic context within the vast indifference of physical law. The Earth that exists at the end of our journey bears no resemblance to the world that gave birth to the first cells, nurtured the evolution of complex organisms, and eventually produced minds capable of contemplating their own existence across geological timescales. The continents have drifted into new configurations that would render our current maps meaningless. The atmosphere has been stripped away and reconstituted multiple times through processes that dwarf the most dramatic climate changes in recorded history. The oceans that once covered 70% of the planetary surface have boiled away into space, leaving behind only crystalline plains that preserve in mineral form the chemical memory of vanished seas. Most profoundly, the biosphere that represented Earth's most remarkable achievement, the transformation of sterile rock and primitive atmosphere into a living system capable of evolution, consciousness, and creative response to environmental challenges, has been eliminated entirely. The last organisms, clinging to existence in deep subsurface refugia, have succumbed to conditions that exceed the adaptive capacity of even the most resilient extremophiles. The planet has returned to the sterile state that characterized its earliest history, before the emergence of life introduced the possibility of systems that could evolve, reproduce, and manipulate their environment in pursuit of continued survival. Yet this apparent ending reveals itself, upon deeper contemplation, to be only one movement in a much larger symphony of cosmic evolution. The processes that transformed Earth over the past 500 million years represent merely a preview of changes that will unfold across even vaster timescales as stellar evolution carries our Sun through the remaining phases of its nuclear lifetime. The red giant phase that awaits in another 4.5 billion years will dwarf the environmental changes we have witnessed, expanding the solar atmosphere to encompass Earth's orbit and reducing the planet to a cloud of vaporized elements dispersing through interstellar space. Even the destruction of Earth and the eventual death of the Sun represent only local events in the much larger story of cosmic evolution. The Milky Way galaxy, which has served as the backdrop for our solar system's entire history, continues its own evolutionary journey through gravitational interactions with neighbouring galaxies, the formation and destruction of stellar populations, and the slow dance of spiral arms that creates and eliminates favourable regions for planetary formation across galactic timescales that stretch across tens of billions of years. Within this vast context, the story of Earth life assumes both cosmic insignificance and profound meaning. From the perspective of galactic evolution, the 4 billion year experiment in biological complexity that flourished on our planet represents a brief flicker of organised activity in a predominantly sterile universe. The genetic information accumulated through eons of evolutionary innovation, the cultural knowledge developed by conscious beings, the artistic achievements that captured beauty and meaning in temporary forms, all of these accomplishments appear destined for complete erasure as the physical substrates that supported their existence are eliminated by processes that operate on scales far larger than biological systems can influence or resist. Yet this same cosmic perspective reveals the extraordinary improbability and precious nature of the biological experiment that Earth represents. Among the countless planets that orbit stars throughout the galaxy, the subset that develops conditions suitable for the emergence of complex life appears vanishingly small. The precise balance of stellar luminosity, planetary mass, atmospheric composition, magnetic field strength and orbital stability required to maintain liquid water and stable surface conditions for billions of years may be so rare that Earth-like worlds represent unique experiments in cosmic organization. If this is the case, then the termination of Earth's biosphere represents not merely the death of one planet's living systems, but the elimination of patterns of organization and information processing that may never again be replicated in this region of the universe. The loss encompasses not only the immediate destruction of ecosystems and species, but the permanent elimination of evolutionary lineages that carried forward genetic information accumulated across billions of years of adaptation to environmental challenges that tested the limits of biological possibility. The question that emerges from this contemplation cuts to the heart of consciousness's relationship with cosmic time. What does it mean for temporary beings to possess the cognitive capacity to understand their own impermanence within larger systems that operate according to principles indifferent to their survival? The minds that evolved on Earth through natural selection for immediate survival needs developed, almost accidentally, the ability to comprehend mathematical relationships, physical laws, and temporal scales that extend far beyond anything relevant to biological fitness in local environments. This cognitive capacity creates a profound tension between the immediate concerns that dominate conscious experience and the larger contexts that render such concerns cosmically insignificant. Human minds worry about daily challenges, plan for futures measured in decades, and preserve cultural information across centuries or millennia. Yet the same intellectual tools that enable these practical activities also reveal that all human concerns exist within systems governed by stellar evolution, galactic dynamics, and cosmological processes that will ultimately eliminate every trace of terrestrial civilization. The resolution of this tension may require a fundamental reconceptualization of meaning and purpose that transcends the anthropocentric perspectives that evolved to guide behavior within local social and environmental contexts. If consciousness represents a form of cosmic self-awareness, the universe developing the capacity to understand its own nature and evolutionary trajectory, then perhaps the meaning of conscious existence lies not in the preservation of particular biological lineages or cultural achievements, but in the ongoing process of cosmic comprehension itself. From this perspective, the death of Earth's biosphere represents not an ultimate tragedy, but a transition in the forms through which the universe achieves self-understanding. The scientific knowledge developed by Earth-based civilizations, the artistic visions that captured beauty and meaning in temporary forms, the philosophical insights that explored the nature of existence itself, these accomplishments may represent contributions to a larger process of cosmic awakening that transcends the particular biological systems through which they emerged. The information patterns that constitute consciousness, creativity, and cultural knowledge might prove more durable than the biological substrates that originally supported their development. Advanced civilizations might develop technologies for encoding their essential achievements in forms that survive the destruction of their home planets, preserving the insights and perspectives developed through billions of years of evolutionary experimentation in crystalline matrices, quantum storage systems, or forms of information organization that remain stable across cosmological timescales. Such preservation efforts might allow the essential achievements of Earth's biological experiment to influence the development of other worlds where conditions remain suitable for complex organization. The genetic algorithms that drove terrestrial evolution, the cultural innovations that allowed conscious beings to transcend their immediate biological limitations, the artistic visions that captured universal patterns of beauty and meaning, all of these accomplishments might seed new experiments in cosmic organization that carry forward the most valuable discoveries of Earth's living systems. The possibility of such information transfer across cosmic distances and timescales suggests that the approaching sterilization of Earth might represent not an ending but a metamorphosis. The biological phase of terrestrial evolution, which required the precise environmental conditions that will soon be eliminated by stellar brightening, might give way to post-biological forms of organization that can survive and propagate under much more extreme conditions. These hypothetical post-biological entities might bear no resemblance to anything we recognize as life, yet they could preserve and extend the essential functions that characterized Earth's biosphere: information processing, environmental adaptation, creative response to challenges, and the capacity for continued evolution in response to changing conditions. Such entities might exist as distributed networks spanning multiple star systems, as quantum coherence patterns that transcend material substrates entirely, or as forms of organization that operate according to physical principles we do not yet understand. The development of post-biological organization represents perhaps the most speculative extension of evolutionary theory into realms that challenge our fundamental assumptions about the nature of life, consciousness, and cosmic purpose. Yet the history of Earth's biosphere demonstrates that evolution consistently produces innovations that transcend previous limitations and explore possibilities that would have seemed impossible from the perspective of earlier evolutionary stages. The transition from non-living chemistry to self-replicating biological systems, the development of photosynthesis that transformed planetary atmosphere, the emergence of complex multicellular organisms, the evolution of consciousness capable of understanding mathematical relationships. Each of these developments represented unprecedented innovations that opened entirely new chapters in the story of cosmic organization. The approaching termination of Earth's biological phase might catalyze similarly unprecedented innovations that carry the story of terrestrial evolution into realms we cannot currently imagine. Whether such transcendence proves possible, or whether Earth's biological experiment represents a finite episode in cosmic history, the journey we have completed through 500 million years of planetary transformation illuminates fundamental questions about the nature of existence, meaning and purpose within systems governed by physical laws that operate across vast scales of space and time. The contemplation of Earth's far future serves as a mirror that reflects back the most profound questions about consciousness's relationship with cosmic processes. Why does the universe appear to have developed, through evolutionary processes operating over billions of years, systems capable of understanding their own cosmic context? What is the significance of beauty, creativity, and moral insight within systems that seem destined for heat death and maximum entropy? How do temporary patterns of organization find meaning and purpose within larger contexts that appear indifferent to their survival? These questions possess no definitive answers that can be derived through scientific investigation or logical analysis alone. They represent the boundary where empirical knowledge encounters the deeper mysteries of existence itself. Yet the very capacity to formulate such questions, to feel their emotional weight, and to seek responses that satisfy both intellectual and aesthetic criteria represents one of the most remarkable achievements in the known universe. The minds that evolved on Earth through competitive struggle for survival resources developed, almost as a byproduct of that process, the capacity for mathematical reasoning, artistic creation, moral reflection, and metaphysical speculation that extends far beyond anything required for biological fitness. This cognitive capacity allows conscious beings to participate in the universe's apparent drive toward greater complexity, understanding, and creative expression, even while remaining embedded within biological systems that are themselves temporary arrangements of matter and energy. Standing at the conclusion of our temporal journey, having witnessed the transformation of a living world into sterile desert, we are forced to confront the ultimate questions that consciousness poses to itself. What does it mean to be aware of our own impermanence within systems that transcend our understanding? How do we find significance in temporary achievements when viewed against backgrounds of cosmic evolution that render all local concerns trivial? What is the appropriate response to knowledge that reveals both the extraordinary improbability of our existence and its apparent cosmic insignificance? Perhaps the answer lies not in resolving these tensions, but in embracing them as the defining characteristics of consciousness itself. To be aware is to exist suspended between immediate concerns and vast contexts, between local meaning and cosmic indifference, between creative possibility and thermodynamic constraint. The experience of this suspension, with all its accompanying wonder, terror, and beauty, might represent the universe's most remarkable achievement: the development of systems capable of experiencing their own existence as simultaneously meaningful and absurd, precious and insignificant, creative and constrained. The Earth of 500 million years hence stands as a monument to impermanence, a sterile world that preserves in its geological structure the fossilized remains of evolutionary experiments that once produced living systems of extraordinary complexity and beauty. The crystalline plains that mark the graves of vanished oceans, the wind-carved landscapes that replace the forests and grasslands of biological epochs, the silence that has replaced the symphony of countless voices that once filled air and water with the sounds of life. All of these features serve as reminders of the ultimate transience of even the most successful adaptations to environmental challenges. Yet in contemplating this transformed world, consciousness demonstrates its most profound capacity: the ability to find meaning and beauty in processes that transcend individual survival, to appreciate patterns of organization that persist across scales of time and space that dwarf personal experience, and to participate through understanding in the universe's apparent drive toward greater complexity and self-awareness. The echoes of our world will persist long after the last traces of biological activity have been eliminated from Earth's surface. They will resonate in the gravitational patterns that record the planet's interaction with other bodies in the solar system, in the isotopic signatures that preserve evidence of ancient biological processes, in the orbital mechanics that carry the sterile Earth through its continued journey around an aging sun. More significantly, they will persist in whatever forms of organization and information processing emerge from the cosmic experiments that follow Earth's biological phase. Whether through direct preservation of terrestrial knowledge, through the influence of scattered terrestrial organisms that somehow survive to seed other worlds, or through convergent evolution that rediscovers similar solutions to the challenges of organization and awareness in hostile environments, the essential achievements of Earth's living systems may continue to influence cosmic evolution long after their original biological substrates have been eliminated. The ultimate echo of our world lies in the questions that consciousness poses to itself about meaning, beauty, and purpose within systems governed by mathematical relationships and physical laws. These questions, once awakened in the universe through evolutionary processes operating over billions of years, may prove more durable than the particular biological systems through which they first emerged. They represent the universe's growing capacity for self-reflection, aesthetic appreciation, and moral consideration. Capacities that may transcend the specific material arrangements that originally supported their development. In this sense, the death of Earth's biosphere represents not an ending but a graduation. The transformation of local biological experiments into more universal forms of organisation and awareness that can survive and propagate under conditions far more extreme than those that supported the emergence of life on any particular planet. The consciousness that evolved to contemplate its own cosmic context may ultimately transcend the cosmic limitations that currently constrain its development, achieving forms of existence and understanding that fulfill rather than contradict the deepest aspirations that have driven evolutionary innovation throughout the history of life on Earth. The echoes of our world will thus resonate not as nostalgic reminders of what has been lost, but as promises of what might yet be achieved when temporary arrangements of matter and energy develop the capacity to understand and transcend their own limitations within the vast systems of cosmic evolution that continue to unfold across space and time scales beyond current comprehension. In contemplating the death of Earth, we participate in the birth of possibilities that extend far beyond the boundaries of any single world, any particular species, or any specific arrangement of stellar and planetary conditions. The silence that will eventually characterize Earth's sterile future may prove to be not the absence of meaning, but its transformation into forms that transcend the particular sounds and sights and experiences that currently define our understanding of what it means for the universe to be aware of itself. The echoes of our world will speak in languages not yet invented, through forms of beauty not yet imagined, toward purposes not yet conceived by minds still constrained by the biological heritage that gave them birth, but need not limit their ultimate development.